project is hardware and loop V2X simulation. Testing and validation of cooperative driving have some challenges. Testing in the real world is costly and risky, and simulation done in discrete time intervals. Our solution is to couple the VUT operating in real time with large-scale VANET simulation in order to test and validate cooperative driving application. This is our system architecture. The vehicles under test can be controlled by a human driver according to the sensor inputs of customized commands like V2S messages. Since it is complex to implement a vehicular environment using a number of such real vehicles, we use a traffic modeling simulator to add the traffic into the simulation environment. The VUT is inserted into a simulated vehicular environment that is generated by the traffic modeling simulator. After combining the VUT with the traffic environment, it is integrated into the communication environment to allow communication among the simulated vehicular nodes. Then the V2S messages received by the application layer of the node representing the VUT inside the communication environment is transmitted back to the VUT. It is controlled according to the data that is received from the communication environment. This is the data flow of our simulation environment. Mobility and the road network data is exchanged through the upper TCP IP link. The messages received by the application layer of the node representing the VUT in the communication environment are transferred to the VUT controlled in webhost via another new TCP IP client server connection. For this link, Omnet++ is the client, while the webhost is the server. Webhost continuously listen to the port and Omnet++ sends the message just after they are received by the application layer. After receiving the messages, the webhost controller processes them and gives commands to the vehicle as required by the application. A simple car following application allowing a single lane straight road verified that and validates the integrated simulation environment. This figure illustrates the car following application. The blue vehicle is the leading vehicle and drives with the speed profile as shown in this figure. The maroon vehicle, the lagging vehicle, which follows the leading vehicle using a control algorithm based on the message received from the leading vehicle. In this scenario, only the lagging vehicle is controlled with the received V2S messages. This is the demo for car following application. It is implemented for two scenarios where the lagging vehicle is either a pivot vehicle or sumo vehicle. The leading vehicle has given a speed profile. Speed of the lagging vehicle in each of the scenarios is plotted in this figure. The reason for this variation is that sumo vehicle is updated every 100 milliseconds, while the webhost vehicle is updated every 10 milliseconds, which gives more realistic behavior as continuous changes. It verifies the system that webhost vehicle shows the realistic behavior with small time step, while sumo follows the discrete events. Next, we consider the webhost vehicle as the lagging vehicle and then add packet losses of 20% and 50%. Likewise, V2S messages are lost in a random way where the number of percentages out of the messages received in no packet losses scenario. The variation of speed from no loss scenario increases with the increase of packet losses. Then we see some applications running on our simulated platform. Platooning show that the integration simulation environment can be used to evaluate mixed traffic scenarios with one vehicle operated in real time added to simulated traffic. This is the demo for platooning application. Another application is eco-driving application. This application is implemented on our simulation platform to see behavior of vehicles with eco-driving and human driving. Length of 5 km, single lane straight road is considered as the road map, while 4 traffic lights are implemented randomly at distance of 616 meter, 1361 meter, 2446 meter, 3491 meter, 4146 meter from the starting point from the vehicle. This is the demo for cooperative eco-driving application. On normal location, the vehicle is controlled by human driving algorithm, but here in cooperative eco-driving application, the vehicle is controlled by eco-driving algorithm. Then after running two simulations for eco-driving and the human driving, the variation of speed of the vehicle in each scenario is plotted in this figure. By looking at this plotted figure, we can observe that the fuel consumption in human driving behavior is higher than the eco-driving scenario. After running simulation for two different vehicle models, the total fuel consumption has been plotted in this figure. Finally, we can use our simulation setup for simulating real vehicle dynamics, evaluating different vehicle models, comparing human and autonomous driving, and analyzing mixed traffic scenarios. Thank you.